and I'll be presenting for the HGeiger Data605 Final, starting with problem set 1. So now let's move into full screen mode. So here's the data. There's 4 x variables, 4 y variables, each in a column here. And the idea is to pick 1 x variable and 1 y variable to answer all of the questions. So the first question is, if we're looking at the first quartile of our x variable and the third quartile of our y variable, calculate the probability. The first probability is that x is greater than the first quartile and or y is greater than the third quartile. Second one is for both of them to be greater than their respective values. And then the third one is the probability of x less than the first quartile and or y greater than the third quartile. Second question is just to fill in a count of the values corresponding to the cutoffs in question 1. And then question number 3 is if we instead use the thresholds of first quartile for y as well, and then check how often x is greater than the first quartile and or y is greater than the first quartile, and see if they're independent or if those two events seem to be correlated. So just going to start with question number 2, and then we can use this count table actually to work on question number 1. So on top are the calculated probabilities, and the bottom are the theoretical probabilities assuming independence. So here we have 20 observations. By definition, you're going to have 5 observations less than the first quartile, and also 5 observations greater than the third quartile. So you can multiply the probabilities. For example, x is less than the first quartile is 5 over 20, and then y is less than the third quartile would be 15 over 20. So if you multiply those two probabilities, you end up with something equal to 3.75 over 20. And then you can repeat that for the other ones. And in the end, you see that actually the calculated probabilities are pretty similar to the theoretical probabilities if the probability of getting x less than the first quartile is independent from y less than versus greater than the third quartile. So I thought that was interesting. And then you can just use those counts to calculate the various probabilities. So when you have this OR operator, it actually is equal to the sum of a few different probabilities. So for example, x is greater than first quartile or y is greater than third quartile. So you can sum either where only one of them is true or both of them is true. And that first question you end up with 15 out of 20. And then so on. You can see here, you just take those counts and you can break it down where if it's an OR operator and there's actually different separate events, combinations where that can be true to calculate the total probability. Then you can make a similar count table for problem 3, but just here, the lowercase y is actually the first quartile of y. There's also no values where you have anything exactly equal to the first or third quartiles here. So you can actually just have less than and greater than, and you don't need to have equal to on either column or row. And so those are the counts there. And again, if you compare to the theoretical, it's pretty close to the theoretical probabilities. So that suggests that the chi-squared test is going to have a high p-value because the idea is that if the two events are independent, then it should be pretty close to just selecting by chance. And we do indeed find that to be the case. You can just take this table and put it right into the chi-sort test function in R, and you get a p-value of 0.37. So that confirms these are independent. It's pretty much random whether you're going to see these together or separate or not. It's pretty equal to just the combination of the population probabilities for each one separately. So now moving on to problem set 2. So this is the Kaggle housing data set. So using regression to determine the sale price from 79 features. There's a variety of features in this data set. It's from a town in Iowa. And some of them are classical numerical features, for example, lot front area or just total lot area in square feet. You also see some categorical, like whether the foundation is concrete versus cinder blocks versus something else. Then there's count data, where it is numerical, but it's actually counting a physical item, such as the number of bathrooms. The categorical variables often have many levels in this data set. So, for example, there were 25 different neighborhoods. Some of the neighborhoods had a lot more homes sold than others. Some of the levels are kind of nominal, but also have an order to them. They're not exactly numeric, but they're not exactly like regular nominal like a neighborhood would be either. So for example here, this is quality or condition from poor to excellent. You have poor, fair, average, good, and excellent. There are also some intentionally missing variables that had to be converted. So some of them were missing, but it was actually just because the home didn't have a basement, so there was no basement quality rating. But then that actually indicates something. So I made that into its own level. Then the continuous numeric variables that there are in the data are often right skewed. So for example, this is square feet of the first floor and the second floor. On the right, it's showing it only for the homes that have a second floor. But you can see most of them are towards the lower end. But then you do have a few homes that have 3,000, 4,000, 5,000 square feet on the first floor that are much larger than the other homes. There are those outliers. So then I ran a correlation of a few different variables with the sale price. So I just pick ones that seem like they would be correlated with sale price. So there's this first floor square feet variable, and then there's also GR live area, which is the above ground living area. Those are both very correlated with sale price. Makes sense. Then there's this lot area variable, which is the area of the lot that the house is on. Also correlated with sale price, though less strongly. That variable is very skewed, so I also just took a snapshot looking only at the homes minus those very high outliers for lot area. You still see a correlation, but it's not quite as clean a line as for first floor square feet and above ground living area. Then I also wanted to take a look at an example of some numeric variables that might also be correlated within the independent variables. And you see that the first floor square feet and the above ground living area are very correlated. In fact, they're often identical because if the home doesn't have second floor, then a lot of the time those are going to be identical. Both of those are correlated with lot area as well, which also makes sense. The correlation there isn't quite as strong. Actually, in the final data set, I ended up eliminating this above ground living area variable because it's just perfectly collinear combination of first and second floor square feet, basically. So I ended up eliminating that. And this is an example of how you could see that doing correlation scatter plots within your independent variables. So here is the correlation matrix. So you see there's a pretty high correlation here above ground living area and first floor square feet of 0.566. Then you can also run a hypothesis test. So the idea is that, so to see if the correlations are non-zero, I mean, it's pretty obvious that it is here, but you can actually test that statistically. So the idea is that if you had a population and you were taking a sample from that population of the two variables, the idea is that even if they were actually not correlated at all, the true population value is 0. If you take a sample just due to chance, it could make it be where it's not exactly 0. So you run this hypothesis test to say, theoretically, if you took a sample from the population for those two variables, what's the chance that this is actually just due to random chance and that the actual population value is 0, and you're seeing something here that's some variation from 0 just due to chance. But the p-value is extremely small. They really seem to have at least some level of correlation. This is shown for the most correlated variables. But even for the other ones, they were all very significant. You can also get this confidence interval and to get kind of a range of where you think the correlation is. So that idea of if you took samples from the population, what would the correlation be? And here, so the value that we get is 0.566, but we can also put a confidence interval around that of around 0.54 to 0.588. So you can also, if you invert that correlation matrix, you get these variance inflation factors, which is basically a measure of collinearity within your variables, and you can do that by just running the simple solve function in R to invert the correlation matrix. And then this was just kind of a side thing to review linear algebra. So if you run this LU decomposition function, you can, if you run that on a matrix, so the task here was to run this on the correlation matrix, and the idea is to get a matrix where the lower matrix has zeros above the diagonal, and you can see that here, and then the upper matrix has zeros below the diagonal, and then the idea is that if you run multiple matrix multiplication of lower times upper, you get the original matrix, and you'll see here, that's the correlation matrix. So then now moving on, again, just to review, so what's an exponential distribution? So it describes events that can occur continuously and independently at a constant average rate. So the minimum is 0, so you can't have negative values, and the probability quickly goes down as the values increase. Shown as an example for a rate of 1 out of 10, for example, something where you have, say, a failure rate where it's supposed to be every 10 years. So even if something's not actually an event occurring over time, you could model it based on an exponential distribution. So shown here is if we took the lot area variable and we treated 1 square foot as corresponding to this number. It's a pretty small number, units of time. So shown is the histogram of the original versus the fitted values. And then it's kind of hard to see with the original values. Most of them were less than 20,000. So on the right is just a similar panel plot, but with the original values just showing the ones less than 60,000, since there's only a handful more than 60,000. You can see there are some differences. Particularly the fitted distribution has more where lot area is in the range 0 to 5,000. And then also you see the max of the fitted distribution is much less. You don't have those very high outliers, which is kind of the point of fitting one of these standard distributions, such as the exponential distribution, to your data. So I actually took this a step further. So that was just fitting a distribution, just showing a theoretical distribution based on exponential with that lambda. But you can also do a fitting where you take the value that is the first percentile in your actual data, and then you say if there's an exponential distribution with that lambda, what's the first percentile value in that theoretical distribution? And then this is comparing the actual values to the fitted values. And you'll see that the fitted values are lower than the actual values when the actual values are either very low or very high. And then the fitted values are higher than the actual values when the actual values are more towards the middle. And this is kind of what you want. You kind of want to make it so it's not so skewed. That's kind of the point. And could this kind of transformation actually be helpful when building your model? And actually, it seems like it might be. So the fitted values, where you fitted to an exponential distribution, seem to have a better correlation with sale price, which is the target. If you actually calculate correlation coefficients, it seems to be a bit better as well. So that's something nice. I didn't actually end up doing that in the final model, but this shows that this can actually be a helpful thing to do in real life when you're running a regression. So now on to the actual modeling for the Kaggle competition. So one important step is to create dummy variables. So I use the model.matrix function in R to create dummy variables. So this variable has levels fair, average, good, and excellent. And the idea is that you then have a column that says, is this average? And there's a 0 if it's not average, if it's fair, good, or excellent. It's a 1 if it's average. And then you have a similar column for good and excellent. You drop whatever the first level is here. So if something were fair, it would be 0 for average, 0 for good, and 0 for excellent. In this case, this is an ordered variable. I use dummy variables, but you might also want to convert that to numeric instead. You could do 1, 2, 3, 4. I use dummy variables, and for some of the other variables, for example, if it's foundation, brick, cinder block, or concrete, then you have to use these dummy variables since there's no order to it. There's no sensible way to make that numeric. Then also looking at correlation within the independent variables. We talked about this a bit before, but this is showing for select very correlated variables. Blue is a positive correlation, red is a negative correlation. And this showed that we had to remove some variables, which I ended up removing that weren't obvious at first. But for example, there's this variable sale type, and then sale condition. And the condition is actually called a partial sale if the home is still being built. And so those were pretty much entirely collinear. So that was an example of things that might not be obvious at first unless you really read through the data description. But you can also find that by running these correlations. And I was able to remove that variable so you don't have these two variables that are almost always going together in either the positive or negative direction. It's going to mess up your model. So running this kind of plot lets you know which variables you need to remove, and then I remove them. So then also there were a lot of missing values for this lot frontage. So basically the area in front of the home had a lot of NAs. So you can use this step function, which is automated backward selection, where it starts with all the variables, and then it gradually removes them to get a select set of variables where they're all significant. And so I use this function to remove NAs from the lot frontage variable, where I modeled lot frontage against the other variables, and you get things like lot area is correlated with lot frontage, first and second floor square feet. I also found some other people online in this competition were taking the square root of lot area. So since it's so skewed, you can account for that skew and then better model the lot frontage, which is very correlated with the lot area. So I actually, before I was even getting to the main model, I built a model to remove the NAs from lot frontage using the step function. So then once I did that, and there were some other NAs I had to remove, but that was the main one that was really a lot of NAs in the data. So then I had all my variables. Then I applied the same step function to do backward selection to start from the beginning and then get down to only significant variables for sale price. And then made some residual plots. And the model, using the step function to model sale price as a combination of some of the other as a function of some of the other variables. So on the left is the index. So this is ordering the actual sale price from lowest to highest. So if you order the sale price from lowest to highest, and then you look at the residuals within the range of the actual sale price, it's relatively constant. You see a few extreme values, but overall, the magnitude of the residuals seems pretty similar, whether the actual values are on the very low or very high side, which is what you want. And then this is a density plot, and the residuals appear relatively normal. It's pretty even whether you're going to slightly over or underestimate. So I thought this looked pretty good. So then the question was, how did I do in the actual Kaggle competition? So actually didn't do so great in the Kaggle competition. So the previous plots I showed were on the training data, and then you have the test data. So my Kaggle score was actually quite high. You want a lower Kaggle score. Mine was on the higher side, 0.62307, which is a bit strange because my adjusted R-squared for my model was so high. And even if that R-squared was somehow inflated due to collinearity within my variables, my residuals from the training data also seemed pretty small. You'll see here, it's not like I'm frequently off by like 50, 100,000. They're seemed pretty close to me. So if I'd had more time for this assignment, and I might do this on my own in the future, I might try and split the training data up. So the idea would be to take part of the training data, build a model based on that, and then try and predict for the other part. So then this way, I would also have a test set where I actually know the answers, and maybe I can figure out what I did wrong. I did some releveling of some of the factor variables. Maybe I got a little carried away with that. For example, I tried to group the months sold into seasons. Maybe I tried to get a little too fancy, and I should have just kept it simple. But I might try that again in the future. But I thought this was really interesting, working with data that had so many factor variables and making the dummy variables. And then this data set also has a lot of collinearity and learning how to deal with that. It was an interesting challenge, and had some fun with it. And thank you, Professor Fulton, for your time with this class. Thank you.